Assalamualaikum. We are from Group 6. Our topic today is defect and solid, which is explain how imperfection in material can influence their physical and mechanical properties. These are my group members: Hazim, Nabil, Afika, Aizira, Najiha and Omul. The objective of our presentation are as follows. First, we aim to define what crystal defects are and understand their basic concept. Second, we will explain the different types of crystal defect that occur in solid material. Third, we will discuss how this defect can change or influence the properties of materials, such as their mechanical and electrical properties. Next, we will look at real-world application where crystal defects play an important role in material performance. Finally, we will show clear example using visual to help everyone understand the concept better.
According to the third law of thermodynamics, a perfect crystal is the most stable form of a solid, especially at absolute zero temperature. Imperfect crystal atoms or ions are arranged in a very orderly and close-packed way. This arrangement gives the solid the lowest possible energy, but in real life, perfect crystals does not exist. The structure of a crystal depends on several factors. These include the charge of the atoms or ions, the type of bonding, and the size of the particles. These factors decide how atoms are arranged in the crystal. Okay, so why do crystals have defects? In real solids, some atoms may be missing, some may be extra, and some may be out of the position. These irregularities are called as crystal defects. Crystal defects can happen because of vacancies in lattice, movement of atoms from their normal positions, non-stoichiometric composition in ionic solids, and impurities added during crystal growth. Point defects are formed due to high temperature and thermal agitation, impurities inside crystal, radiation damage, and mechanical stress. The common types of crystal defects are Frankel defect, Schottky defect, interstitial defect, and vacancy defect. To conclude, real crystal always contain defects. These defects affect the properties of solids, such as strength and electrical behavior.
Based on our finding, defects are defined as a deviation from the perfect atomic arrangement in a crystal structure. In a real material, a perfectly arranged crystal rarely exists. This defect can occur due to several factors such as high temperature, radiation exposure, manufacturing process, intentional doping, and mechanical stress. Although they are called defects, they play an important role in influencing the properties of material. Defects are especially significant in metal, ceramic, semiconductor, and mineral, where they affect how the material perform in real-world application.
Stoichiometric defect. Point defect are imperfections that occur at or around a single point in a crystal lattice. First, we have a vacancy defect. A vacancy defect happens when an atom is missing from its normal position in the lattice. Because an atom is missing, the density of the substance decreases. For example, in sodium chloride at high temperature, chloride ion can leave their atomic sites, creating vacancies. Next is interstitial defect. This occurs when an atom occupies a position in the lattice that is not normally occupied. In a perfect crystal, as extra atoms are added into the structure, the density of the substance increase. A common example is carbon atom present in iron, such as in steel. Lastly, we have substitutional defect. This happens when a foreign atom replaces a normal lattice atom. This type of defect can change properties like color and hardness. An example is brass, where zinc atoms substitute copper atom in the lattice. Schottky defect. A Schottky defect occurs when one cation and one anion are missing from their regular lattice site in an ionic crystal. Because ions are missing, the density of the substance decreases. However, the crystal remains electrically neutral because equal numbers of positive and negative ions are lost. A common example is sodium chloride, where equal numbers of Na plus and Cl minus ion are missing. Next, Frankel defect. Frankel defect happens when an ion moves from its normal lattice site to an interstitial site within the same crystal. Since no ions are lost, the density of the substance does not change, and electrical neutrality is maintained. An example is silver chloride, where the Ag plus ion move to an interstitial position.
For non-stoichiometric defects, there's two types, which is metal excess defect and metal differentiation defects. For metal excess, it's separated in two parts, which is an ionic vacancies and extra ion. So, in ionic vacancies, it occurs when missing an ion from its regular site, leaving a hole which is occupied by electron to maintain the neutrality of the compound. Example is NaCl, where in a perfect ionic crystal, each Cl negative ion occupies a fixed position. Due to thermal agitation, irradiation, or crystal growth imperfections, a Cl negative ion may leave its lattice site. This creates an empty anion site called an anionic vacancy. While for extra ions, it occurs because of extra ions occupying interstitial sites, while electrons occupy another interstitial site to maintain electrical neutrality. It is quite similar to Frankel defect, which means displacement of an ion, but metal excess defect means an addition of ion plus free electrons. Lastly, metal differentiation defects is arise due to cationic vacancy. It occurs when positive ions are missing from its lattice crystal site. For example, is NaCl, because in imperfect crystal, each cation Na plus or sodium occupies a fixed lattice position. Under certain conditions such as high temperature or non-stoichiometric composition, some cations leave their lattice site. This results in vacant cation sites known as cationic vacancies. Next, we move to line defect dislocation. For line defect dislocation, it occurs of four components, which are edge dislocation, screw dislocation, effect on properties, and visual cue. For edge dislocation, it occurs when an extra half plate of atom is inserted into the crystal. This creates a local distortion in the surrounding lattice structure. The distortion reduces resistance to movement, allowing atomic layers to slip more easily when stress is applied. While for screw dislocation, it occurs when an atom are arranged in a helical or spiral pattern around the dislocation line. This structure is formed due to shear stress acting on the crystal. It produces shear deformation, allowing layers of atoms to slide past each other parallel to the dislocation line. Then, effect on properties happen when increasing the ductility, where dislocations allow atoms to move gradually, making metal easier to be shaped without breaking. It also enables plastic deformation because the movement of dislocation allows metal to deform permanently under applied stress rather than fracture. Lastly, it can cause word hardening. As deformation continues, the number of dislocations increases. Dislocations interact and block each other movement, making the metal harder and stronger but less ductile. Lastly, visual cue occurs when stress is applied. Then dislocations move through the crystal lattice, allowing layers of atoms to slip past each other, causing the metal to bend and deform plastically.
Surface or plane defects. In surface or plane defects, we have three types, which is grain boundaries, stacking fault, and twin boundaries. For the effects, the smaller grains is harder, metal hold patch effect, control strength, hardness and tautness, and the last is important in steel and alloy design. For real-world applications, first we have semiconductors. In semiconductors, the defects plus doping controls conductivity. For the example, Si doped with P into N type. There is no control defect equal to no modern electronics. For the second, we have ceramic. In ceramic, there is no oxygen vacancies enable ionic conductivity, and we use in solid oxide fuel cells. Third, we have metal, dislocation engineering, stronger structure. Cold working at this location is increased in strength. For the last, we have color centers. F center give color to crystal. For the example, sodium chloride turns into yellow and Li doped crystal will turn into pink.
Now that we know what defects in solids are, let's focus on the importance of studying the defects in solids. Defects play a major role in mechanical properties. For example, dislocations can strengthen metals through work hardening, but defects can also act as sites for cracks, which may lead to material failure. Second, controlling defects allow engineers to design materials with desired properties. For instance, high-purity silicon with control defects is vital for producing reliable microchips. Studying defects is essential because it helps us predict how and when materials might fail, such as through fracture, creep, and fatigue. By preventing or controlling these defects, we can improve the reliability and lifespan of material used in everything from buildings and bridges to electronic devices and machinery.
The last one is a conclusion. According to the third law of thermodynamics, a perfectly crystalline solid represents the most stable and odorless state of matter. However, such ideal crystals rarely exist in real conditions. In reality, all solid contain crystal defects due to the thermal agitation, impurities, mechanical stress and radiation damage, and non-symmetric composition. These defects, such as vacancy, interstitial, Frankel and Schottky defect, are irregularities in the crystal lattice where atoms or ions may be missing, displaced, or present in excess, and they strongly influence material properties including mechanical, strength, hardness, electrical, and ion conductivity, diffusion, behavior, density, and optical characteristics. Although extensive defect can weaken material, an optimal and controlled introduction of defect enables essential processes such as atomic diffusion, plastic deformation, and charge transport, and is crucial in modern material design. For examples, in semiconductor, doping, and the strengthening of alloy and ceramic. Therefore, crystal defects are not merely imperfections but fundamental features that determine material behavior and enable the development of advanced materials for technological application.